Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. Thank you everybody for coming for what should be hopefully the last talk of this marathon talk week. Today we have Ethan from University of Washington just across the lake, and Ethan's going to actually tell us about, and his thesis work is kind of very interesting. He's solved some long-standing problems with the internet, but in a very practical and usable manner, and he's going to tell us about that. But apart from a really good networking researcher, I can testify he's also a really good skier. He spent a few years being just a ski bum somewhere in Utah or Montana, I forget. And I've seen him ski. He's very good, so that's kind of another reason for us to, get him here. We can improve our average skiing level, yes.
I'm also happy to take questions about skiing if there's anything particular that you're working on. I was a ski instructor, so I can pass on some of this.
Go for it.
Thanks, Ratul. Thanks, everybody, for coming. So I'm going to try to convince you that the internet is much less reliable than it needs to be, but that we can make substantial progress both in improving its availability and performance without requiring any architectural changes. And I'm just going to talk about a set of distributed systems that I've built to get us towards that. So I want to start out just with a simple survey. Can you raise your hand if you've used email or used the internet since you got to this room? All right, so some people. How about in the last hour? More people? Today? I think it's probably just about everyone. Anyone who didn't raise their hand is probably just busy checking right now, so didn't actually notice that I was asking them anything. So my point is that we rely on the internet. And I think even though we all know that we depend on the internet, it's still astonishing when you see some of the actual numbers. So over a quarter of the world's population is online today. In the time that it's going to take me to deliver this talk, humankind collectively is going to spend over a millennium on Facebook. And actually, in the 10 minutes that it took me to put together the statistics for this slide, Kanye West sent 3 new tweets. There's also a lot of money involved. So companies like Google, like Microsoft, are making billions and billions of dollars in ad revenue. And because we depend on the internet so much, we really need it to be reliable. So traditionally, we've used the internet for applications like email, like web browsing. E-commerce sites have depended on it being reliable in order to deliver their business. Now we're accessing data and applications in the cloud. We're using the internet to watch movies, to make phone calls, and we really want our cloud data to be reliably available. We want our movies and phone calls to be smooth. But I use Skype to try to do meetings with my advisor sometimes, and we've all experienced having to hang up multiple times before it works well. And in the future, we're moving towards a world where we're even more dependent on the internet. We're going to have more of our applications in the cloud. We're going to have most of our communication over the internet, and we're going to want to run critical services across the internet. For these applications, we really need to be able to rely on it. We need high availability, and we need good performance. So we can just ask, are we ready for that? I'm going to show you that the current answer is no, but that we can take some concrete steps towards improving it. So I'm going to start out just by talking about the current situation. So actually, we all check internet availability every day. Seems like usually most things work. Sometimes they don't work. But each of us is only checking from, we're only seeing a small slice. We're maybe checking from work, we're checking from home. And there's actually hundreds of thousands of networks that we could be checking. Places like Facebook, Microsoft are having people working full-time to try to maintain availability, but they still struggle with these problems sometimes. So we can really ask, what about everybody else? I decided to assess reachability on an internet scale continuously. I built a system called Hubble that checked over 100,000 networks around the world, and it checked them from a few dozen computers around the world. Each of these vantage points would periodically check to see if its routes to all the other networks still worked. All of these networks were available from all of the vantage points at the beginning of the study. And as I started making these checks, I realized that there were problems happening all the time, all around the world. At any point in time, there are locations all around the world that are reachable from some places and not reachable from others. So this is a snapshot that was generated automatically by my system Hubble. Each of the balloons here represents a network that had previously been reachable from all of the Hubble vantage points. It had become unreachable from some of the vantage points while remaining reachable from others. So we know, since it's still reachable from some, that it's not just the other networks offline. And these partial outages really shouldn't happen. There's some sort of router configuration that's keeping some of the vantage points from being able to reach the destination. So in this case, the darker the balloon, the longer the problem had lasted. So the lightest colors, the yellow, those have been going on for up to 8 hours. The darkest colors, the maroon, those have been going on for more than a day. So there's these really long-term problems that aren't being fixed. And if you're actually behind one of these problems, you're basically stuck.
Sure. How do you know it's a router configuration issue and not just not having enough redundancy at the level of policy, right? Like a link could fail and you could just disconnect it without any kind of configuration error.
So we know that it's not just a hardware failure because hardware failures can only result in this partial reachability if there's a network partition, and there's not a partition because both the one that could reach and the one that couldn't can talk to University of Washington. It could be policy, and the policy is encoded in the router configuration. So in that case, it's not necessarily a misconfiguration, but it's an issue with the configuration of routers. In other words, if they reconfigured the routers, changed the policy, then it would become reachable. So I'm not getting super specific about it, whether it's a misconfiguration or not, but it has something to do with configuration. It's not just a fiber cut.
So are these all Planet Lab nodes?
We were checking from Planet Lab nodes to every network that we could find a pingable address in.
So these balloons are just some network address in certain edge network?
Yes, yeah.
And how do you check the availability?
So we, the vantage points each periodically ping to see if the destination is still responsive. If it isn't responsive from one of the vantage points for a couple pings in a row, then we trigger trace routes from all of the vantage points, and we see whether the trace route reaches the network. So we don't care if it reaches the particular end host. We just see if it reaches the network. So in all these cases, there were some trace routes from some vantage points that reached the network, and in most cases also reached the end host. And some of the other trace routes weren't even getting to that edge host, so they weren't getting the whole way across the internet to the network.
So are these problems close to the edge network, or is somewhere in the middle of the internet?
So many of them are fairly close to the edge, but they're not right at the edge, because if it actually reaches the last network, then we don't consider it a problem anymore. Somewhere in the middle, I honestly don't have a great characterization of how many were in the middle or how many in the edge, but I think the instinct that a lot of them were towards the edge is right.
Yeah, I think once the failure is at the edge, because the IP to ISP mapping could often have some problem. So maybe it's problem just either in the edge network or between the edge and the upstream ISP.
So we tried to eliminate as many of those as possible by using every available technique for mapping to the correct AS. And it's certainly possible that some of these cases were issues like that. But some of them, when you actually looked at them by hand, were obviously happening closer to the middle of the internet.
So,
can I just want one more sentence on Ming's question quickly? There are some statistics in the paper on how many looked like they were in the last but one AS, and I don't remember the numbers off the top of my head, but it wasn't all of them, and so those other ones, it couldn't be this boundary issue, at least at the edge AS, because it wasn't even looking like it was in the previous one. Yeah, sorry.
okay, so there's two possible. I'm trying to understand which two cases here, which is these networks you can't reach. Is it the case that one of your sample points at least one of your sample points can't reach them, or that all of your sample points can't reach them?
So it's the case that some can and some can't, and we had a threshold for a couple not being able to, because if just one did, then it could just be a problem with that particular vantage point.
In every case, at least someone in the sample set could reach it.
Yes. We track the ones that are completely unreachable, but for the ones on this map, they're partially reachable, because those are the more interesting cases. So in fact, it's not just these outages that matter. Sometimes you can actually get to something, but it's just too slow to use. And providers are aware and concerned about these slow routes. So I have up here statistics. Google published a paper in 2009, and one of the stats they had in there was that 40% of the connections from Google clients had a round-trip network latency of over 400 milliseconds. And that's just the network latency from the client to the Google data center, and then from the data center back to the client. It doesn't include any processing at the data center or at the client. And this is even though Google has data centers all around the world and tries to direct each client to the one that gives us the lowest round trip time. So to give you some idea of 400 milliseconds, it's as if the traffic was leaving the client here in Seattle, going around the equator to the data center, and then leaving the data center and going around the equator again before it goes to the client. These slow routes have a direct impact on business. I have up there a statistic from Yahoo. An extra 400 milliseconds of latency led to an additional 5 to 9% of people clicking away from the page before it even loaded. And this leads to a direct loss in business. So these huge companies have slow routes, even though they have a big monetary incentive to have high performance. They need a way to try to understand these problems, and they currently lack the means to guarantee performance. Yep.
So 400 milliseconds is really big. Based on the measurement we did from our data center to the edge of the network, almost this is the maximum RTT we can observe. I suspect most of these problems are due to the latency at the last hop rather than on the internet. If the latency at the last hop, there very little you can do to circumvent that.
Sure. So they had some further statistics. Again, that's not. I'm not trying to say that that result is what I would say is bad routing. It's just trying to point at the problem that they're concerned about. And they had some more statistics in the paper when they tried to break that down. It's a good paper with a read. They found that I think so. That statistic was on client connections. They also looked at prefixes, and I think they found that 20% of prefixes had what they considered to be an inflated latency that was addressable through routing means. So the current internet doesn't deliver reliable availability or performance. It means that we can't really use it for critical services. And if you talk to operators at major providers, you learn that they end up spending a lot of their time trying to explain and fix these problems. There's been lots of interesting and important work done on how we could redesign the internet protocols to improve this situation. And in fact, I've worked on some of that. But we're also really stuck with the internet that we have now. We need to improve the internet that we've got because there's so many entrenched interests. We want to improve the services that exist on it now and then enable future services. So I'm going to show you how we can actually do that without requiring any changes to the protocols or the equipment. There's two components to my approach. First, I build tools that provide better information, and operators can use these to troubleshoot the problems. Once you have these tools, I build complete systems that use these new tools as well as the existing ones to try to help move us towards an internet that can actually fix itself. The problems that I address really arise from routing. They're difficult to detect, diagnose, repair. I'm going to explain why later in more detail, but for now there's two big issues. First, the internet is one of the most complicated systems that humankind's ever built, and it has emergent behavior. And second, it's a huge collection of these independent networks. They have to work together to enable routing, but the operators don't necessarily share information. So to improve this situation, we have to address a range of research challenges. We have to be able to understand topology and what routes are available. We have to monitor availability and develop ways to improve it. And we have to understand performance and troubleshoot problems. I've worked on systems to address all of these challenges. Today, I'm just going to talk about a few of them just for time reasons. I'm going to talk about my reverse traceroute system, which lets you measure the path that anybody's using to get to you. And I'm going to give a brief example of how you can use it to troubleshoot performance problems. And then I'm going to talk about a set of techniques that I'm working on to address availability problems. So that gives the basic outline of the talk. In order to understand the work, I'm going to first have to walk through some background on how routing works and what tools are currently available, just so you can understand how the problems arise. And it's going to be very high level. Most of you are already going to know it. Then I'm going to talk about reverse traceroute. It's a measurement system that I built that provides information that you really need to troubleshoot the types of problems that I'm talking about. I'm going to show how operators can start using it to debug performance problems. And then in the final talk part, as I said, I'm going to turn to availability problems. I'm going to talk about some systems that I'm working on now that use reverse traceroute to make steps towards automatic remediation of outages. So I want to make sure we have the same basic view of what the internet looks like. It's a federation of autonomous networks. Each of these clouds is one network. For a client up at the University of Washington to talk to the web server down at the bottom there, traffic is going to traverse some set of these networks. Within each network, it's going to traverse some set of routers. Now, many of these routes tend to be stable for pretty long periods of time. Even like days and days is fairly common. I'm going to give an overview of how these routes are established. So BGP is the Border Gateway Protocol. It's the internet protocol to establish these inter-network routes. The way it works is the web server's ISP will advertise the set of addresses that is available. It'll tell this to its neighbors. So now AT&T has learned a route. So now AT&T has a direct route to the web server's ISP. It'll advertise that to its neighbors. Now Level 3 and Sprint have routes through AT&T to the web server's ISP, to the web server. They're going to advertise those on. So now University of Washington has learned two routes. Now, one key with BGP is that routes generally aren't chosen for performance reasons. BGP lets each network use its own arbitrary policy to make decisions, and it's an opaque policy, so it's generally going to be based on business concerns. So in this case, let's say University of Washington has a better deal from Level 3, so it chooses that route. So now traffic from the client at University of Washington to the web server is going to follow some path like this.
And the whole path is transmitted up. So UW can actually make a decision. say it doesn't want any track to go through Sprint.
It sees a network level path, yes.
It sees the whole, but it sees the whole.
Yeah, it receives a message that essentially looks like that and has which addresses are at the end of that path. Exactly.
But at some point it just sends an IP packet and it doesn't control this.
Yeah, it's not necessarily enforced that it'll follow this path, but it at least is seeing the route that it thinks it's selecting.
I guess you don't have a good case in here, but if you had a case where, depending on whether it went through L3 or Sprint, that there was a third network, that if it went through Sprint, it wouldn't go through the third network, but if it went through L3, it would go through the third network. It sees enough information that it could decide to send packets through Sprint so they didn't go through that third
Yeah,
network.
and that's a great example of the opaque policy. It's allowed to use whatever policy it wants to make its decisions.
Next hop. It's not source routing all the way.
That's what, but it could.
But it could make decisions based on what appeared in the path. It generally doesn't, but it could.
But there is sufficient information in the protocol that it could, right?
Yes.
But it can't actually specify. The only
gets to specify the next hop.
It can't enforce the path that it takes, but it could select the path based on where it thought it was going to go and try to avoid these paths if it wanted to. So another consequence of this policy-based routing is that paths are often asymmetric. The way that can arise is the University of Washington will advertise what addresses it has available with a path that just says, hey, send it to the University of Washington. It tells that to its neighbors, so now Level 3 and Sprint have direct paths. They're going to advertise that onto AT&T, and again, AT&T can use whatever policy it wants. Let's say it prefers the path through Sprint. It's going to select that path, advertise that onto the web server's ISP. Web server's ISP has a path through AT&T to Sprint to the University of Washington. So now traffic back to the client will go this way. We have asymmetric paths. So portions of the paths may overlap, but generally they're often at least partly asymmetric. Now, each of those clouds that I had represents a network, and in the case of big ones like AT&T or Sprint, they actually span multiple continents. Each of those networks is made up of routers, so we have to go from this inter-network path to a router-level path. Here we have the University of Washington's path that it selected, which went through Level 3 AT&T to the web service ISP. I have a representation of the Level 3 network, shown in red, AT&T shown in blue. One possible path through this network looks like this. So Level 3 carries it across the country, then gives it to AT&T. That might be the shortest path through the network. But again, the individual networks aren't going to necessarily be optimizing performance across the internet. So it actually might be more likely that the traffic goes like this. Level 3 is going to give it to AT&T as soon as it can because it incurs costs for carrying it. This way, AT&T will incur the cost of carrying it across the country. So the point is that the end-to-end performance that you get and also the availability that you get depends on the inter-domain routing decisions and also the intra-network routing decisions. This means that the types of problems that I'm talking about are problems with routing. So a performance problem might be a geographically circuitous route like this. And an availability problem might be when you have a route advertised in BGP, but when you actually send traffic along it, it doesn't reach the destination. So we're going to need to drastically improve the performance and availability to enable these future applications we want. So we really need a way to understand routing to try to troubleshoot the problems that arise. One attribute of the Internet's protocols is that they don't naturally expose that much information. So you might have good visibility into your own local network, but it's hard to tell what's happening in other networks. Furthermore, those other networks don't really have an incentive to tell you what's going on. So if Sprint has a problem, they don't really have an incentive to inform AT&T exactly what the problem is. This means that we need tools that can measure the routes given the restrictions of what the protocols and what other networks are going to make available. So Traceroute's one such tool. Probably many of you have used it. Traceroute lets you measure the path from the computer that's running it to any network. And it's widely used by operators and researchers. I'm going to give a basic overview of how Traceroute works. So all internet packets have a time to live or TTL field. The source sets this to some value. Each router along the path decrements that by 1. If it hits 0, the router is going to throw out the packet, and it's going to source an error message and send it back to this original source. So Traceroute's going to manipulate these TTL values to build up the path. Here, we're trying to measure the path from S to D, and the first thing Traceroute's going to do is send out a packet and set the TTL to 1. It's going to get to some first router, say F1. F1 decrements the TTL value to 0. It's going to discard the packet and generate an error message. It's going to send this error message back to S, and when S gets the error message, it can look at it, see that it came from F1, and now it knows that F1 is the first hop on the path. And then Traceroute's just going to continue this process. It's going to send out a packet now, TTL2, gets to F1, F1 decrements it to 1, sends it on, gets to some F2, F2 decrements it to 0, throws out the packet, sources an error message, sends it back to S. Now S knows the path goes through F2, and we can just continue this until we've built up the whole path. So if operators at the web server think that they're having problems with some client, they can use Traceroute to measure the path to the client. But as we said, routes on the internet are generally asymmetric, and the problem could be on the path from the client back to the web server, and Traceroute doesn't give any visibility into this path. First of all, the client's computer is going to be the one setting the TTL value, and it's going to set it to a normal value. So there's not going to be these error messages generated, and the web server's operators don't have any way to control that. And then even if there were error messages generated, they're going to go back to the client, and so the web server isn't going to observe them. Now I'm going to give a real example of how that limitation affects operations. I'm then going to show how we can address this limitation with my reverse traceroute system without requiring any modifications to existing protocols or equipment. I started out with some statistics about how many slow routes Google was observing, and they built a system to try to address this. So this is an example taken from their paper about that system. In this example, they had clients in a set of networks in Taiwan, shown in red there, and they were experiencing really slow network latencies of 500 milliseconds. So the main thing that Google does to try to have good performance to their clients is replicate their content at data centers around the world and send the client to a nearby one. So the first problem that their system looks for is maybe actually the client's being served by a distant data center. And they can actually look at the logs at the data center. In this case, they verified, in fact, the client was being served by a nearby data center in Asia. Another potential problem is that the route from the data center to the client could be really indirect. But their system was able to verify with Traceroute that actually it was taking a really direct path from the data center to the client. Now the communication's two-way. Paths are likely asymmetric. So at this point, they assume that the problem is on the reverse path from the client back to the data center, but they don't have any visibility into that path. So what they concluded was to more precisely troubleshoot these problems, they needed the ability to gather information about the reverse path back from the clients to Google. In fact, there's been a widespread recognition of the need for this reverse path information. So I attended a network operator's troubleshooting tutorial, and I have up there a quote from this tutorial. The number one go-to tool for troubleshooting is Traceroute, but asymmetric paths are the number one plague of Traceroute, and that's because the reverse path itself is completely invisible. So you can get a good idea about a problem when it's on the forward path, but you're really flying blind if it's on the reverse path. That gives the motivation for our reverse traceroute system. We want a way to measure the path back to us from the client without requiring control of the client, and we want it to require no new functionality from routers, and we want it to use only existing internet protocols. So this is my reverse traceroute system that I built, and now I'm going to walk through the basics of how it works. So here's the setting. We want to measure the path from D back to S. We control S, and we can install software there, but we don't control D. So the first thing that you might ask is, why not just install software at D? And actually, a few years ago, we had extensive conversations both with Microsoft and with Google to try to convince them to do something like this. And they really weren't willing to do that, to get the information that way. They wanted a way to work with what was available and enable operators to fix the problems without requiring the participation of the client at all. So okay, what can we do in this setting? Well, we can measure the forward traceroute, but the path is likely asymmetric, so it's not clear that gives us that much information about the reverse path. The next thing that you might think to do is use other computers around the world that we actually do control, and that's what we're going to do. We do have access to other vantage points. In my case, I use Planet Lab, which is a test bed that gives you access to computers at a couple hundred universities around the world. These aren't going to directly give us the path from D, but they're going to give us a view that's unavailable from S, and also we can combine the view of the multiple vantage points to get a better view than is available from any one of them. There's only a limited number of them, so what can we do with them? Well, we can start issuing trace routes to them, to destinations around the world. We can build up like an atlas of what routing looks like. And one set of paths that we can measure are the paths from our vantage points back to S. Our idea is to use the fact that internet routing is generally destination-based. What this means is the path from any place in the network depends only on where the packet is in the network and where it's going. It doesn't depend on where it came from. So this means that if we intersect one of these blue paths that we know about, we can assume that we follow it the rest of the way back to S. So these paths aren't going to give us the full path from D, but they're going to give us a baseline of paths that we can use to bootstrap off of.
So how do you deal with the ECMP load balancing plans to the same destination?
So there are a couple options there. We can use, or we do use Paris traceroute-like techniques to try to expose the multiple options that are available. And then when we return a path, you can return the multiple options. The other thing is that people have relied on traceroute even given these sorts of multipath limitations now. And so I think just building a reverse traceroute system that gives you a view into at least one of the paths is a great starting point, and now we're starting to look into techniques to expose the multiple paths.
What's content providers, let's say Akamai, provide any kind of reverse traceroute service?
They don't make that available, and most, Akamai has pretty good visibility, but even then, they can't necessarily measure the path from arbitrary routers where they don't have a presence, and anyone else who isn't Akamai is going to have many fewer points of presence than that, so they're not even going to have that view that Akamai does.
I guess my assertion is Akamai probably has better edge coverage than Planet Lab.
Akamai certainly has better edge coverage than Planet Lab, but I'm going to show you how we can use Planet Lab's vantage points, the limited number of them, and actually bootstrap them to get much better coverage than you'd think we might be able to. So now we need a way to build from D until we hit one of these paths that we know about. And actually, destination-based routing is going to help us do that also. If we're able to learn that the path from D goes through some router R1, because of destination-based routing, we only need to measure the path from R1 back to S. We can ignore D. So this means that we can build the path back incrementally. If we learn that it goes from R1 through R2 and R3, now we just have to measure from R3 back to S. If we learn it goes from R3 to R4, now we've hit a path we know about. We can assume that we follow V1's path back to S, and we've successfully stitched together the path incrementally. So I left out one key piece, right? How do we get each of these segments that we're stitching together? We need something in the internet that's going to let us measure a path a hop at a time. And IP options are going to give us that. IP options are a built-in part of the internet protocol. You can enable them on any packet, but we're the first to recognize that you can use them to build a reverse traceroute system. The first IP option that we're going to use is the record route option. Record route allocates space in the header of the packet for up to 9 IP addresses. The first 9 routers along the path will record their IP address. Now, the key with the IP options is that they're going to be copied over into the destination's response. So if we reach D within 8 slots, the remaining slots will fill up on the reverse path. So to give an example of that, let's say that the paths look like this. With record route, we can get these yellow hops. We get 5 hops on the forward path, the destination for the 6th hop, and then the remaining 3 slots fill up on the reverse path. This is great. So if we're near enough to use record route, we can get a few hops at a time and stitch together the path. The problem is that the average path on the internet is about 15 hops in each direction, 30 round trip. And so what are we going to do if we're too far away to use this?
So how many routers actually respect the R option?
So the best place to look for statistics on that is there was a SIGCOMM 2008 paper called Discart by Rob Sherwood. I don't know the exact number off the top of my head, but essentially they found that there was widespread enough coverage that we started thinking about what to use record route for that could enable some of these. There certainly might be some networks where we don't have good visibility into them. The key is that because we're just trying to measure back until we hit one of these traceroute paths that we already know about, we often don't have to measure that many hops.
So in your study, do you
Yes.
find the majority of the paths support this R option?
There are some networks that do, there are some don't, lots and lots do. I think that, I believe that the coverage just in terms of networks that support it is over 50%, but I don't know the exact number off the top of my head. I'm going to have some results later on in terms of accuracy, and you can sort of infer from those that we're getting good coverage out of our techniques because we are able to measure the paths using the combination of techniques. Whichever order.
Which is not supported. Does the packet just get copied with the existing recorded routes, or do you lose all the information?
So there are different.
If the failure mode is that you get nothing, or you get these silent routers that don't appear in the route.
Sure. So there are potentially both behaviors. There are some places where the packet will be filtered and dropped. There are other places where it might be forwarded and just you won't see that particular hop. Similarly with traceroute, there are some routers that don't source these TTL expired packets, and so you get some blind hops there. So in the Discart paper, they have some statistics quantifying how many routers have each of these different behaviors, and that's sort of what we built off of for that. In our paper, we have some statistics on these reasons, like how many hops might be hidden from traceroute, how many might be hidden from record route.
The destination operating system networking stack has to respect record route and understand on a response that it has to fill in the previous receipt?
Yes.
Okay. And that's widely supported too? Like, does Windows support it?
I believe so. We don't tend to probe to nhost. We probe to the router right before the nhost because that last hop will be symmetric anyway. But it's a built-in part of the IP protocol, so in general, everyone has to support it. We've certainly, I mean, our machines, we tend to test on Linux and certainly support it there. So this is going to work great if we're close. In the case when we're not close, that's where we use the fact that we have distributed vantage points. What we can do is find a vantage point that's close to the destination. So let's say in this case that V3 is close to the destination. It's going to send out the record route probe, but it's going to spoof, which means that it's going to set the source address to S's address. So we're the first to use this source spoofing to sort of separate out the forward and reverse path and measure reverse path information. So what's going to happen here? V3 is going to send the record route probe to the destination. When it gets there, some number of the slots will be filled out, let's say 7. D will add itself in, and then it's going to reply, but it thinks that the packet came from S, so it's going to reply back to S. When the packet gets back to S, S looks at it, it's now learned that R1 is on the reverse path. So this source spoofing is going to let us use any vantage point that's close to the destination, regardless of whether or not it's the particular source that we're trying to measure to. And now, because of destination-based routing, we can just repeat this process. Now we need to find a vantage point that's close to R1. Let's say that V2 is close to R1. It's going to send the packet, spoof, and claim that it came from S. When it gets back to S, we've now learned that R2 and R3 are on the reverse path. Now, we have to measure from R3 back. And suppose we don't have a vantage point that's close to R3. We might still have some idea about what the set of possible next hops are. And that's because, as I said before, we're measuring paths from our vantage points to destinations around the world to build up an atlas of routing. So we can look at this atlas, and let's say previously we've observed a path like this. We've observed another path like this. This means that R4 and R5 are good candidates for where this path might go next. So now we need a way, given one of these likely candidates, to verify which one is right. And we're going to use another IP option to do that. We're going to use the timestamp option. The timestamp option lets you specify up to 4 IP addresses in the packet. And if routers with those IP addresses are traversed in the sequence that you specify, then they should record their timestamps. The key here is that it's ordered. So the way we're going to use this is S is going to send out a timestamp probe to R3, and it's going to ask first for R3's timestamp and then for R4's timestamp. Because they're ordered, if R4 is traversed on the path going to R3, it won't record a timestamp because R3 hasn't recorded yet. So this packet's going to get to R3, R3 is going to record a timestamp, and then it's going to reply back to S. When it gets back to S, in this case, let's say that R4 has recorded a timestamp, we now know that R4 was on the reverse path. So we don't care about the particular value of the timestamp, we're just using it as a check of whether or not that router was traversed. So we now know the path goes through R4. We've intersected a path that we know about. At this point, we're going to assume with destination-based routing that we follow V1's path back, and we successfully stitch together the reverse path. So I've now shown you how we can address this key limitation of traceroute and measure the reverse path, even though we don't have control of the destination. There are a number of keys. Yep?
A lot of access networks won't allow packets out that have source addresses that are not on the access network to prevent that kind of spoofing. So do you find that that's a problem with a lot of the, for example, Planet Lab networks?
So it's certainly the case that spoof probes are filtered some places. The most complete study of that is from MIT. They have this spoofer project where you can check from your machine whether or not you can spoof. They found about 25 to maybe a third of, 25% to 33% of sources can spoof. We found similarly with Planet Lab. The key here is that you just need, well, if a particular vantage point can spoof, it can generally spoof as everybody. And so you just need a set that can spoof that are well distributed, and you can bootstrap the whole system off that. You don't need any particular vantage point to be able to spoof.
Okay, so you just throw out immediately any vantage point that happens to not be able to...
Yep, we check which ones can, retain the ones that can't, and I think it's on the next slide. We use about 90 right now. So we're using these multiple vantage points to get a view that's not available from any particular one, and we're using spoofing to let us select the vantage point that's in the best position to make any particular measurements. You need to address a number of things to actually make this technique work well. So for instance, some routers don't process these IP options correctly, but we're able to account for these incorrect processing and still get useful information in many cases. We have techniques for doing that. Similarly, some ISPs filter some of the probe packets, and we have techniques to avoid some of these filters and improve the coverage of the system. Finally, you want to be able to measure without having to issue too many probes, and we have techniques that let us intelligently select particular vantage points so that we can sort of maximize the return on any particular probe that we send. So Reverse Traceroute is a real deployed system. I think as of this week, we're issuing around 100,000 reverse traceroutes a day. In our current deployment, we're using about 90 Planet Lab and Measurement Lab sites as our vantage points. We're using Planet Lab sites as the sources. So this means that you can now measure paths back from anywhere to Planet Lab. You can actually try out the system with a few sources at revtr.cs.washington.edu. Now, when none of our vantage points is able to measure a hop from a particular destination using any of our techniques, we have to make an informed guess for that particular hop and then measure back from that one hop. So this means that the coverage that we get is actually tied to the set of vantage points that we have. What we found in evaluating the system is that you actually need the full set of techniques to get good coverage. So if you don't use timestamp, or you don't use record route, or you don't use spoofing, the coverage will immediately drop enough that you no longer have a useful system. The overhead of the system is reasonable, both in terms of the amount of time that it takes to make a measurement, in terms of the number of probes. It's about 10 times that of traceroute right now. I'm going to go into a little bit more detail in accuracy. So operator, yep.
Just wondering, do you have a sense of the shelf life of reverse traceroute with respect to where the trends are as to what the routers are doing, like with these option processing and timestamps? Is there a longitudinal sense at all?
So there was a study done a number of years ago where they concluded that IP options weren't supported enough to be useful. In recent years, Discart used record route, we've used timestamp and record route, and we've seen better usage than they did previously. So I think that the trends are in our favor. Also, I've talked about this system to many operators, like I've presented at operators conferences, and lots of them are signing up to use the system. And I think that hopefully that should lead to sort of goodwill within the operations community, where best practices are to enable these options so that you can make these measurements, just like best practices now are to support traceroute in your network so that other people can debug problems that they're having. So because operators are used to using traceroute, we'd like our system to return equivalent results to if you actually had access to the destination and were able to issue a direct traceroute. Now, we don't have access to ground truth information for the internet as a whole, but we can actually evaluate this in a controlled setting. So we're going to look at paths between Planet Lab nodes. We're going to compare a reverse traceroute to a direct traceroute. For the reverse traceroute, we're going to assume that we don't have control of the destination, use the technique that I just outlined. For the direct traceroute, we're just going to log into the destination, issue a traceroute. We can compare those two paths. This graph shows the result of that comparison. On the x-axis, we have the fraction of the direct traceroute hops that you see. And the graph is a CCDF. So any particular point on the graph says that it gives you the fraction of the paths that had at least that fraction of accuracy. Right now, without access to reverse traceroute information, operators fall back to assuming that the forward path and the reverse path is the same. So the black line gives how well you do if you just assume the path is symmetric. In the median case, you get 38% of the hops right. So you're really not getting that much information. The red line is our system. In the median case, you get 87% of the hops correct. And so this whole shaded region is the benefit of our system.
So have you tried the traceroute servers, which have even bigger coverage than Planet Lab?
We use traceroute servers as part of our system. You can't issue the options probes from them, but we actually use them to build up our traceroute atlas.
I mean, for the validation purpose.
Yeah, we have results on that too in the paper. So the line, if you sort of find the traceroute server path that's the closest to the one that you're trying to measure, the line is somewhere in the middle there. And we also use those in evaluating accuracy, just as we did Planet Lab to Planet Lab paths, we did traceroute server to Planet Lab paths. And the results look almost the same. The line is, a couple percentages different.
Sources of imprecisions.
So the two main sources are that, so an ideal line, just so make sure everyone's on the same page with reading the graph, is a vertical line at x equals 1. So what this graph shows that in most cases we get most of the hops right. There are two main reasons we don't get that vertical line at x equals 1. The first is that routers have multiple IP addresses, and it can be hard to identify if two IP addresses are on the same router. So one technique might be observing one IP address, another technique might be observing another IP address. So in those cases, we're essentially undercounting. We're getting it right, but we just don't realize it. The second main source is that when we're not able to measure, when we don't have coverage of a particular network, we have to assume that that particular hop is symmetric and measure from that one hop back. So this means that the accuracy of our system will improve as the coverage grows. And in fact, I've helped Google deploy a version of reverse traceroute now, and they have access to more vantage points than I do. And so as you would expect, they get better coverage than I do in my system.
So what about the AS level accuracy? Here is the IP level accuracy.
So in the paper, we evaluate pop level accuracy, so sort of in between those two trends. And the pop level accuracy, I believe in the median case, we get 95% of the pops right. Maybe, actually, it might even be 100% of the pops right. It's in that range. I helped Google do an evaluation on AS level accuracy, and essentially what you see there is that in cases where you have the coverage and are able to make measurements from every hop, I think it's like 98% of the time you get the AS path right, and most of the time when you don't, it's sort of off by one, so it might be the sort of cases that you're talking about where you're unclear on the boundary which AS you're actually in. So I've shown you now how we can build a working reverse traceroute system. I started out with this problem that Google was having with their clients in Taiwan, and now I'm going to walk through an example of how you can use reverse traceroute to address problems like that. So in this case, I measured a round-trip latency of 150 milliseconds from a Planet Lab node in Florida to a network in Seattle, and this is about 2 or 3 times what you might expect. Now, the network's in Seattle, but it wasn't affiliated with the University of Washington. It's just sort of random that it happened to be there. With traditional tools, what an operator would do is issue a forward traceroute and see if the path is indirect. So that's the first thing that I did. So if you look at this path, you see that it starts in Florida, goes up to DC, comes back down from DC to Florida, and then continues across the country. So this detour up to DC and then back down to Florida is explaining about half of the inflation. But with traditional tools, you only get a partial explanation. It seems like the rest of the problem is on the reverse path, but you really have no idea exactly what's going on or who to call to get it fixed. With reverse traceroute, we can actually measure that path. So that's what I did. So if you look at the reverse path, you see it starts in Seattle, goes down from Seattle to LA, comes back up from LA to Seattle, and then it continues across the country via Chicago. Now, if you look closer at this path, so this detour down to LA is explaining the rest of the inflation. If you look closer at the path to see what's happening, it's starting out in Seattle on Internap. It's going down on Internap to LA. In LA, it's switching over to transit rail, coming back up to Seattle on transit rail. So it's not necessarily a misconfiguration. It could actually be that transit rail and Internap only connect down in LA, and so the traffic has to go down there. But I was able to verify with a traceroute from the University of Washington that actually they appear here in Seattle as well. And I was able to talk to operators at these ISPs. They verified that this was an unintentional configuration. So it might be that maybe it was out-of-date information or something like that. This type of misconfiguration is a common cause of these routing problems, and it's effectively operator error. There's this manual reconfiguration going on all the time. It's easy to get it wrong. It's hard to understand the consequences of any change you make. It's hard to understand the interactions of your change with the rest of the network. Without access to both directions of the path, you really have no way to understand what's going on or who to contact to fix it. With access to reverse traceroute, even I, as a grad student, was able to talk to people who could fix this path.
Talking to the people seems to be the problem, right? How do you call up the ISP and get the right person on the phone? That's a much harder problem.
It's a different type of problem, right? So I started motivating. It would be hard for me as a grad student to go around debugging all the problems of the internet using this tool. But actually, in the Google system that I used to sort of motivate this section of the talk, that's actually what they're trying to get. Is they want something to point at the problem, and their assumption is once they can point at the problem, they can do something about it. They can, call it. They have the clout and the connections to call them up, or they can change the routes, or they can install more capacity, or whatever it was. So the main thing that they wanted was a way of classifying what the problem was, where it is.
It seems like you have the tool, which is show me from one network the entire rest of the world, every place where there are large differentials and where the routes are going. I mean, a global view of this, right? Instead of kind of debugging it one by one.
Yeah, and so that's essentially
be able to generate the list of, here's all the networks that have got to go be fixed.
Sure. So this was me debugging one particular path. The paper that they have at IMC 2009 is essentially that system, and the problem is that system needs reverse path as part of its input, and it didn't have it. So that's how they do it, and presumably people at Microsoft do something similar where you want to prioritize where the problems are and come up with solutions that can fix multiple problems and things like that. So the lack of reverse path information has been identified as a key limitation by Google, by operators, by researchers. You really had no way to get this information before, so anyone who cared about internet routing was really only seeing half of the information. I've now built this reverse traceroute system that lets you measure the path to you without control of the destination, and I gave an example of how you can use it to debug performance problems. Google is now starting to use it in that context. Reverse traceroute is also useful in a range of other settings, including availability problems. And I'm now going to talk about how we can...
Move on.
Yeah.
I'm curious. This whole tool was developed as end user, from an end user's point of view, right? Why the network operators doesn't use something? Because they have access to the router. Excuse me. If they really want to inject something there, it's a lot easier for them to do it. Is there no incentive for them to do it? Or?
They have access to routers in their own network, but they don't have access to routers in other people's networks, and the people in the other networks don't have much incentive to give them much information about what's going on in their router.
It's a big problem. Why don't the network operators sort of join together and solve it?
So public traceroute servers, which Ming talked about, are sort of a step towards that. Networks make available a website. You can go and issue traceroutes from their vantage point, but there's only about 1,000 of those. And I think it's just hard to get to the type of coverage you really need to debug problems across the internet. One direction of my work that I'm not really going to talk about today is we're starting to look at what are small tweaks you might make to the IP protocols, so maybe a new IP option that we can add or something like that that would make some of these measurements easier and expose some of that information. And we're hoping that we can eventually get buy-in, but it's a long, slow process to get any of that. To have that work at the scale that they need, you need to get standards changed, you need to get router vendors to buy in, you need to get everybody to upgrade their routers to support that, so it's just not going to happen immediately. And the stuff I'm talking about today is really how can we start solving these problems right now using what's available right now. Did you have another?
Just a quick follow-up. I mean, in some sense about the incentives, right? It seems there's already enough incentive for the different ISPs to support, for example, traceroute, like the standard traceroute.
Right.
And obviously, the reverse one would be harder, right? But in some sense, I mean, if there was no incentive whatsoever to collaborate, in some sense, right? They could not even support that. Right?
There's sort of this tension where I think the operators are often willing to cooperate, but then there's also parts of the company that So I mean, I presented all this work at operators conferences before I even wrote the paper to try to get buy-in, and I think there's been dozens of operators signing up to try to use the system, things like that. So I think that once they see that you can start making these measurements, it's sort of like that quote said, people viewed it as a fundamental limitation that just this information was invisible. Once you start showing them how you can actually see it, the hope is that we can get better support, get people buying in, and then maybe eventually move towards easier solutions for providing this type of information. So now I'm going to talk about how we can start to build a system around reverse traceroute that's going to automatically identify, locate, and avoid failures. And it's all work in progress, so I'm going to sketch out where we are now, where we're going with it. I'm going to start out with an example of what operators do now. So this is a quote from an email to a network operator Outages mailing list that I subscribe to. This operator thought that he was seeing problems in level 3's network in DC, didn't really know what was going on, and so sent an email to the mailing list to ask people for help. And in the email, he included a traceroute. So this is essentially his traceroute. It started out at his home in Verizon in Baltimore. It went down to DC, switched over to level 3's network, and then trailed off. So when the traceroute trails off, it means that he didn't get a response back from the destination. So it looks like maybe there's a problem in level 3 in DC, but assuming that the destination is configured to respond, it could be that the destination isn't receiving the probe. It could also be that the destination is receiving the probe, but the operator isn't receiving back the response. And with traceroute alone, you can't tell the difference between these cases. So what do the people on the mailing list do to help this guy? Well, they start issuing their own traceroutes and sending them to the mailing list. So here's another one of those. So this traceroute starts out again in Verizon, but in DC in this case, switches over to level 3, goes from level 3 in DC to level 3 in Chicago to level 3 in Denver, and then it trails off. So again, at first it looked like the problem is in DC, now it looks like the problem is in Denver. Did the problem move? Are they two separate problems? Are the problems on the reverse path? With traceroute alone, you really don't know which of these cases you're in. And actually, nobody on the mailing list ever indicated that they had any idea what was going on. They just sort of each sent out their traceroutes for a while, and then a couple hours later, the problem resolved, and nobody ever gave any explanation. So we'd really like to do better there. So in ongoing work, I'm taking a 3-step approach to that. First, you need to identify that a problem is going on. So that's monitoring, figuring out the problems. Once you know that there is a problem, you want to be able to locate where in the network the failure is. Once you've located the failure, you'd like to be able to reroute traffic around the failure, even if the failure is in a network that you don't control. So as we saw on that Hubble outages map earlier, many of these problems are lasting for hours, sometimes even days. So if we give operators better tools, they could likely fix these problems much faster. But the outage is still going to persist until it's fixed. And so even with better tools, operators are going to be fixing these problems on a human timescale. We'd really like to be fixing the problems within minutes or seconds instead. So once we have these pieces for monitoring, location, and remediation, we can start putting them together as building blocks for a system that's automatically going to repair failures, and that's what I'm going to talk about. First, I want to give a characterization of the duration of outages. So these are results from a 2-month study monitoring a diverse set of targets around the internet. This graph shows the duration of the problems that we observed. So on the x-axis, we have duration in seconds, and it's on a log scale. It's a PDF, so any particular point on the graph shows the probability of an outage of a particular duration. There's 2 points that I'd like you to get from this. First, most of the outages are short. So 90% of the problems lasted less than 700 seconds. Second point, the distribution has a long, heavy tail. The remaining 10% of outages that lasted over 700 seconds accounted for 40% of the unavailability. So this means to make a substantial impact on improving availability, we really need to address problems across timescales.
Do you have a sense of why the graph, the shape is so weird? Why does it go up and then go down?
As opposed to continuing to go up?
As opposed to kind of go down.
Yeah, why that strange peak?
Oh, you mean why don't you see more much shorter problems?
Well, it seems there's a preference for a certain duration window in this.
Yeah, so it could be, the short-term outages are often caused by routing convergence. It could have something to do with how long routing protocols take to converge. It could also potentially be an artifact of the particular way we measured. I don't know. The only point that I'm trying to get on the graph is that there is a long, heavy tail. I'm not going to talk about the short-term problems today. With the short-term problems, so we're going to take basically we take a 2-pronged approach to addressing these outages. The short ones versus the long ones, and it's partly because you can use different solutions. So you can imagine on long-term outages, you can actually get a human involved to try to repair them. It's not going to work on short-term outages because people aren't going to be able to react quickly enough. And it's also partly because the underlying cause is different. So it's already known that there are these short-term outages after failures during routing protocol convergence. And we actually worked on a system called consensus routing to address those. So in that case, it was pretty well understood that it was a protocol problem. People had already done the measurements, and we just built the system to address it. And today I'm going to focus just on the long-term problems. In that case, they're less understood, so the first thing that we had to do was come up with measurement techniques to identify characteristics of them. So identifying the characteristics of those long-term problems is the first goal here. We want to monitor problems across the internet on a global scale continuously. And I'm going to refer to these long-term problems as black holes. In these cases, there's a BGP path available. When you send traffic, it persistently doesn't reach the destination. So this is the system Hubble that I showed the snapshot from earlier. Hubble monitors networks around the world continuously. And it's a system that I built, but just to save time, I'm not going to go into any details of how it works. I'm just going to talk about how many of these long-lasting black holes we saw over time. So we did a 2-year measurement study with Hubble. We monitored 92% of the edge ISPs in the internet. So what I mean by an edge ISP is one that hosts clients, it hosts services, but it's not acting as a provider for any other ISPs. During that time, we saw over 1.5 million black holes. So each of these cases is a network that had previously been reachable from all of the Hubble vantage points, became unreachable from some for a period of time, and then became reachable from all of them again. This graph shows the duration of these problems. So the x-axis is duration in hours on a log scale. It's a CCDF, so a particular point shows what fraction of the problems lasted for at least some number of hours. So the purple circle there shows that 20% of the problems lasted for over 10 hours. So we were really astounded at how many of these problems they were, how long they lasted, how many of the networks they affected. So over 2/3 of the networks that we monitored experienced at least one of these problems. Dealing with them requires someone first noticing that the problem exists, then they have to figure out what's going on, then they have to do something about it. All of these steps take a long time with current tools. So for example, last month, one of CNN's websites was out for over a week. We'd really like to do better. The first thing we need to do is try to locate one of these problems. So we saw in the level 3 example from the outages mailing list that it's hard to understand failures with current tools because it's hard to understand the output of those tools. I'm going to walk through what we can start to do to get better information there. So up here we have a destination D. It's at USC's Information Sciences Institute. X, Y, and Z are Hubble vantage points around the world. Previously, they'd all been able to reach D. The system detected that there might be a problem. All of the vantage points try to reach it. And what we see is X can still reach the destination, Y and Z no longer can. So what can we do to start understanding the failure? Well, the first thing we can do is just group together the paths. So in this case, we see that paths through the Cal State University network are still reaching the destination. Paths through Cox Communication are failing with their last hop in Cox. So it looks like maybe there's a problem with Cox Communication. But actually, it could be that the traffic is reaching the destination and then it's failing on the reverse path back. Traceroute alone doesn't tell us which direction the failure is in, even if we have symmetric paths. Plus, the paths might be asymmetric, so it's possible that the reverse path isn't even going through Cox. So with traditional tools, we couldn't differentiate these cases. With reverse traceroute, we can actually tell which of these cases we're in. The key is that reverse traceroute doesn't actually require the source to send any of the packets. We can send the packets instead from X. We know that X has a working path to D. So it's going to send the packet, spoof is Z. Because it has a working path, the packet's going to reach D. D is going to reply back to Z. So if D has a working path to Z, then Z should receive the response. And that's what we saw in this case. So now we can use reverse traceroute to measure that complete working path. So now we know the failure is on the forward path. Cox isn't forwarding on traffic to the destination. Now, we'd like to understand what happened to cause this failure. If we only make measurements after the failure starts, like the operators on the mailing list, we don't know what change there was that triggered this. So what we do is build up a historical view of what routing looks like, so then when there is a failure, we can look at what routes look like before the failure. So one possibility is the previous route didn't even go through Cox. The route changed over to go through Cox, and the Cox path never worked. In this case, what we observed was actually the previous route did go through Cox, and it went through a router R. Now it's failing right before R. Y observed a similar path. Previously went through router R, now it's failing right before R. So it seems like there's a problem at router R. It's still advertising the path, but then the path's not working. We only know which router to blame because we're measuring this historical information. And in fact, in most cases, we found that you need to have access to this historical information to understand one of these problems. This is ongoing work. I'm going to present, we're running the system continuously now. I'm just going to give an overview of some of the preliminary results.
So in the last example, you can't really blame R, right? It could be some other router that withdrew the route that R had. If you're trying to do router level localization, that seems hard. That seems, and not correct in a lot of cases.
So, a few things. First of all, we know that R is still advertising some path because the traffic is still going to R. Second, we're not necessarily trying to say that R is responsible for failure. What we're really trying to do is show paths that aren't working so we can start reasoning about other paths that are working so we can route around it. Because we don't control Cox communication. So maybe we can tell them, hey, it looks like there's a problem with R. But really what we want to know is that paths through Cox communication aren't working now so that we can start exploring other alternatives that are working that maybe we can use even though we don't control Cox. And I'll get into how we do that in a second.
I guess the question was like, yes, so I realized the value of identifying Cox as the problem. Like, what I'm trying to get at, maybe just trying to understand, like, is telling Cox that R is the problem, does it buy you anything more than telling Cox that this is the source and the destination that's not working?
So
using you to be the problem.
You can imagine that we might observe other paths through Cox that do work if we had, not in this particular problem we didn't, but there might be other problems where we did. And so it seems like there's some value in saying the sets of routers that the sets of paths that used to go through this particular router aren't working to help narrow down where the problem is, and also to let us reason about other paths through Cox that might be working if we have an alternative of choosing a path, say, from a different peering point that isn't going to go through R. We're not trying to say anything definitive about R. We're just trying to come up with some cause that seems like maybe it explains the problem so that at least we can associate Y and Z with each other. If we didn't know that those previously went through R, then we wouldn't even have a way of associating Y's problem with Z's problem. It would look like they're in different parts of the network because they aren't overlapping at this point.
Doesn't your traceroute information tell you that those yellow paths that you see there, the blue paths,
yes,
you can follow those a traceroute up to, but not to R, right?
Exactly. So the pieces of information that you don't get if you're just using traceroute is, if you haven't measured that historical information, you don't have it.
Right after it.
And then you also don't know that the problem isn't on the reverse path. If you're just using traceroute, it could be.
I buy your argument about why you need the reverse path. You're saying
yes.
Once you got that at that point, I'm really questioning the value of the historical information. It seems like you're following what Bertul is saying. If you go to Cox and you say, look, here are two paths, I can trace route them each up to this point and no further. So these routers, wherever they're pointing to next on this path, they're not getting to. That's a lot of information for Cox to be able to identify the next router.
Sure. Maybe. Let me give a slightly different example that maybe is more compelling that we also observe. We have statistics in the paper on how often. Imagine instead that these paths are going through different networks and both dying right before Cox. if we don't have access to information about what the routes looked like historically or what routes are being advertised, we won't know that those two are converging on the same point. And so there we won't have this common information about Cox. And so we might even try to select a path that bypasses those networks but goes in Cox. And we might suspect in those cases that it wouldn't work. Okay. It's less about, we're not claiming that we're pinning down this is the exact cause. It's more about gathering as many types of information as we can to try to reason as best we can about what's going on. Because you really have such a limited view from externally. So we're running the system continuously now. Just to highlight one point that we've observed. More than 2/3 of these outages are partial. So we have some vantage points that can reach the destination, some that can't. And as I was saying before, these partial outages aren't just hardware failures. It's not just a backhoe cutting a path. There's some configuration that's keeping the destinations that can't reach from being able to find the paths that do work. So in these cases, identifying where the failure is and identifying these alternative paths that exist is a big win. If we actually can give this information to operators, they can get in touch with the networks that seem to be causing the problems, and they can essentially yell at these people until they fix it. But we'd really like to be able to make these repairs faster without requiring the involvement of these other networks that you have to call up and yell at. Working paths seem to exist. They're not being found. It's a big opportunity. How can we find them automatically? In this case, let's say that operators at the web server realized that they were having problems with some of their clients. We're going to look at the easy case first. Suppose the failure is on the forward path. In this case, what the web server can do is just choose an alternate path that doesn't go through level 3. So maybe it'll route through Quest instead. That avoids the failure. They can also direct the client to a different data center that has working paths. The harder case is when the failure is on the reverse path back to the web server.
When you say the web server chooses a different path, do you actually mean the web server's ISP?
Yeah, the web server's ISP. Sorry, I'm sort of... yeah, it's not the web server itself. Maybe I should have named the web server's ISP differently from the web server. So this is the harder case. The operators in the web server's ISP don't directly control which path University of Washington is choosing, but they want a way to signal to the University of Washington to choose a different path that doesn't go level 3. They want to send like a don't use level 3 message. You can imagine this message gets to Quest. Quest already isn't using level 3, so it's not going to change anything for them. Advertisement gets up to University of Washington. University of Washington is using level 3. They'll see this. They'll decide not to use it anymore and route a different way through Sprint. Of course, in BGP, there's no don't use this message. So we need a way that's going to work on the protocol today. Let me show you how we can do that. All the web server's ISP's operators have control over is which paths they announce. And so they want a way to change their announcement that's going to force other people to choose different paths. So what do the baseline announcements look like? Well, in the base case, they're just going to announce that the path to the web server just goes through the web server's ISP. They announce that to their neighbors. Now AT&T and Quest have direct paths. They announce those on. Paths propagate through, and then the University of Washington chooses this path through level 3 to AT&T to the web server's ISP. Here's what the web server's operators can do to change the University of Washington's path. They're going to announce instead that the path goes from the web server's ISP to level 3. They'll announce this on Quest. Quest doesn't really care. They're just going to continue routing to the web server's ISP. Announce that on, so on. Similarly, AT&T doesn't really care. They're just going to keep routing to their neighbor, the web server's ISP. Here's the key. BGP has built-in loop prevention. When you get an announcement, you look. If you're already in the path, you reject that route. So when AT&T makes this announcement to level 3 is going to inspect the route, see that they're already in it, and reject it to avoid causing a loop. So suddenly level 3 doesn't have this route anymore. This means that the University of Washington isn't going to be getting this route from level 3 anymore. So they're going to have to look for other routes. They're getting another route from their neighbor Sprint. So they're going to choose the route through Sprint instead.
So this can be easily used by anybody to launch a DDoS attack to the routing system.
Isn't this how Pakistan brought YouTube offline?
It's equivalent to it, yes.
I mean, so I thought we were trying to move to, I mean, I thought we were trying to move to an internet where this isn't possible.
Right.
So that's one strand of research. I'm doing something. So I mean, it's similar to the argument about spoofing. We're doing this in a controlled manner. In ongoing work, I'm working. I might as well cut over to the next slide since that's what the next slide's saying. I'm working to show how you can do this safely. You can imagine that as we redesign BGP to maybe give you some of these security mechanisms so you can't do things like this, we could also think about how to redesign it to let you make these don't use this announcements better. This particular strand of research is about what we can do today to simulate those don't use this messages, and this is a technique for doing that.
Go back one slide.
Yes.
So isn't, for example, Quest, or let's see, maybe not Quest, I guess.
No, if Quest has expensive links with AT&T and Sprint, they might say, oh, I'll send all my traffic through the web servers.
Yeah, through WS, right? Aren't you going to be Grab?
No,
Grab doesn't show.
So these routes, this is maybe, I maybe should have used a slightly different notation. Each of the routes that you announce is tied to the particular prefix that it's going for. So it's just going to announce this prefix for the address block that includes the web server, basically its own address block. So it won't be saying to get to any level 3 address, send it here. Each of these paths is associated with addresses. So the level 3 addresses will still be associated with the announcements that level 3 is making. These particular announcements are just for this block of addresses that the web server's ISP owns.
But L3 could still service this link through GBLX, right? In your example, I mean, you're taking money away from L3 and handing it to Sprint, effectively on the end, and that could, I mean, you know, there are peering wars, right? People could end up trying to harm each other's businesses by setting out these loops, saying, "Oh, I thought you had a router down, so I just, you know, it's only a few hours, you know, a few $1 million. I routed traffic to someone else, and now it's back. You know, sorry about that." Because you have to have proof. There's a burden of proof that the failure actually exists.
Sure. So that's one of the properties that we're trying to demonstrate with the system, is that you can do this in an understandable way where you can show that there is a failure. You can imagine we can use our failure location system to pin down a failure, and we also have techniques to identify when the failure no longer exists so that you can route back. In this case, level 3 wouldn't be able to route through GBLX. Given this announcement, they wouldn't be able to, because they would be getting the same announcement with level 3 in it with the loop from GBLX. But
I know, but
yeah, so you can
route around AT&T through L3. Right? UW could route through L3.
Sure. So our assumption is that in this case, level 3 isn't doing anything to repair the problem because the problem is persisting. If they had already selected that alternate route, then we wouldn't have had to do this in the first place. And there are certainly issues around how long do you wait before doing this, and we're sort of evaluating those in ongoing work. You can imagine that the distribution of failures says that if the failure is short because they're reconverging to a new path that works through GBLX, then we'll let it go. If the problem is persisting longer, you're not getting your traffic, you want to do this.
What if the link is fixed? What do you do to adapt to the scenario where L3 fixed the link?
So there are these properties that you'd like if you're using a system like this. So we're using this BGP loop prevention as our basic mechanism, and we're starting to evaluate it now. But you want to get properties out of it. Like, you want it to be predictable. You want to know when you can revert back to your old path. And we do have techniques for doing that. In that case, what you can do is announce a less specific prefix without level 3 inserted into it, and then I can continue to monitor over that less specific prefix until the problem is resolved. Once it's resolved, I can revert my announcement.
I just want to quibble a little bit the non-disruptive claim on the slide. Like, would it not disconnect all the singly home customers of level 3?
So I'm not claiming that what I just showed on the previous slide is non-disruptive. What I'm claiming is that we have techniques that we are evaluating that go along with this loop prevention. That's just the basic mechanism, but you can do other things to make it less disruptive, and that's what we're evaluating right now. So in that particular example, you don't want to disconnect people who are singly homed, but if I announce a less specific prefix that doesn't have level 3 inserted in it, then those singly homed customers are still going to be able to use that less specific prefix. So if level 3 starts working, or if some routes through level 3 work, they'll be able to use those. But people who aren't stuck behind level 3 and whose traffic's currently failing, like University of Washington, can explore other alternatives over the more specific route.
So I think you try to use this mechanism to deal with packet failure. I mean, today many web servers already have different locations, and the purpose is to fix packet failure. So if I can redirect client to any server that is reachable, then why do I still need to introduce this kind of sophisticated mechanism that could potentially cause a lot more harm than benefit?
Sure. So if you have alternate data centers that have working paths, you should redirect there. This is for cases when you don't have an alternate path. That's essentially the equivalent of choosing a different path out through a different provider. Just go to a different data center. This is for cases when you don't do that. The cases when you can't do that are if their routing to all of your data centers is similar. Like, you can imagine that University of Washington has these multiple providers, they're going to likely route towards all of your data centers through the same provider. If that provider is not working, you need a way to get them to go to a different provider, or else their paths to all of your data centers are going to be failed. Similarly, there are some people who don't necessarily have access to these multiple locations around the world, or only have a few, and we want ways to enable them to get around the failures too.
Well, but if people I think that the space of people for whom this makes sense is small, and that it's people who are small enough that they don't have geographically distributed data centers, but large enough that they have control over their access network and are making BGP advertisements.
So,
I mean, is there such a person anywhere?
I can say that we've just recently started actually experimenting with this, and the first people we talked to were Amazon because they're local, and they thought that it seemed like a reasonable thing to do in certain cases. They were problems that they've experienced where they can imagine trying to do something like this. And they certainly have multiple data centers.
Yeah, but since they have multiple data centers, it seems like, I mean, there's something about this that sort of smells like router vigilantism or something, and I'm wondering if, I mean, so if you look at spam, there's a group of people who I think jokingly propose, oh, we should just write our own computer viruses that go out and infect computers and fix the vulnerabilities so that the bad guys don't have control over them. That's sort of one strand of research. But then there's another strand of research of, well, why don't we generate blacklists of known bad hosts that ISPs can opt into? It's less sexy because it doesn't have this sort of clever aspect to it, but it seems like something that would cause far less damage and might be more accepted by the operator community is to say, we're going to set up a service where we keep a real-time list of routers that we believe to be bad, and UW could subscribe to that and say, oh, looks like L3 is down according to the service all right around it, as opposed to globally advertising this L3 route without their permission.
So I believe that the approaches are complementary. So we're not going to have a world immediately where everybody subscribes to such a service. There's not such a service available yet. Even once we do, it's going to be hard to get everybody to opt into that. And the web server is still going to want ways to service customers who maybe haven't subscribed to that service. What we're trying to do in this work is evaluate how effective the technique is. If we can demonstrate that it's not that disruptive, which is what we're trying to demonstrate, then maybe it's something that people are more likely to use. It's definitely always going to be like a fallback. This isn't your first line of how you deal with problems, but there are problems right now that aren't being addressed. They're lasting for hours, days. There are networks you can call up who, even if you yell at them, they're not going to fix it. There's going to be networks who you don't know who to call. They're going to be clueless when you do call them, and you want ways to be able to deal with these problems, and that's trying to address this. I don't think that it's the only solution for dealing with outages. You want to direct to other data centers. You maybe want to offer a service like this where University of Washington can learn the information themselves. I think that all these approaches complement each other.
Yeah, that's right. I mean, I buy that there are clueless ISPs, and we have to be able to deal with the fact that they're not going to fix a problem. But just in this diagram, imagine that it's AT&T that was having the failure. L3 has an incentive to serve their customers as best as possible by routing around AT&T if they're having a failure that they're not resolving. And so it seems like the right incentive here is to have each ISP be proactively sort of probing and recognizing that one of the people that's advertising a route isn't following through and actually routing as advertised, and so then choosing an alternative. And it seems like that sort of feels like the right layer to fix the problem, as opposed to the web server that's trying to police every ISP in the world on behalf of its customers.
The level 3, though, would have to police every route from every one of its upstreams to everyone on the other side of it. And it's not necessarily clear that it has a great way of knowing what traffic should be going through it at any point in time. If it stops getting traffic one way, it doesn't know if that's because somebody changed routes. If it is sending the traffic, it's not entirely clear. I mean, it would have to be then everybody would have to continuously be probing in each direction to detect those problems. Otherwise, the web server's ISP is going to need a way to signal to level 3. That's not going to happen anytime.
Continuous probing anyway is being done in a different place, which is at every web server. So
right, but that's the sort of probing that already happens, right? You can already passively monitor your traffic, identify when you have dropouts in clients. I agree that there are other approaches that are maybe nicer ways of dealing with the problems, but any of those is going to require additional infrastructure, require additional people to buy in, and I just don't think that those are going to be available tomorrow, whereas I've already experimented with this. I've been able to do this and change paths on the actual internet, and so this is sort of a solution that you can use. I think that work towards proposing how we might want to redesign protocols or layers we might want to add to address these problems in different ways is it's definitely important to do that, and I've done a little bit of that as well. I think that we also need to solve the problems today, and that's where this piece fits in. So I think through the process that I ended up talking about these 3 main points that we want. But essentially the point is that the loop prevention is the basic mechanism. We have other techniques to try to get some of these nice properties that you want, like not cutting off people who already have working paths, successfully rerouting people who don't, understanding when to stop doing this and when to start doing it. we had the statistic from Hubble before that 20% of outages last for over 10 hours. So that's 600 minutes of unavailability. If we're able to locate one of these problems and generate an automatic response to it within a few minutes, we've decreased the amount of unavailability by 2 orders of magnitude. And that's really the vision that I want to leave you with. Should I skip ahead to the conclusion slide?
Just, yeah, wrap up.
Okay. The internet is hugely important, so we really need it to be reliable. I started out by talking about the fact that the internet has suboptimal performance and availability, and we need a 2-prong approach to addressing this. I talked about 2 systems to illustrate that approach. First, we need better tools for operators. Traceroute has been the most used tool for troubleshooting these problems, but it has this fundamental limitation of not giving you reverse path information. I've built a reverse traceroute system to address that problem. It's really essential to understanding the internet. Second, you need systems that can use these tools to automatically fix problems, and I illustrated how we can start to do that by identifying, isolating, and routing around failures. All my systems are designed to work in today's internet, so it's really about getting as much information as you can by using the protocols in novel ways. Because they work in today's internet, operators are able to directly apply the work, and I've presented both pieces of these work at both RIPE and NANOG, which are the big European and the big North American network operator conference. RIPE and Google are now working to deploy these systems in order to improve the internet and start using them to improve the availability and the performance. Thanks. I'm happy to take questions.
So you focused around the network as a cause of instability in the internet. Do you have any numbers about what are the proportion of sluggishness or unavailability due to network or due to service failures?
It's not something that I've looked at. The focus of my work has been on these inter-domain routing issues. Certainly there are problems at both ends, and you need to be addressing both of them. I guess because this has been the focus of my work, I'm not sure how many problems fall into the other domain versus this one. There's certainly plenty of problems in this domain for people to try to solve, and plenty in the other. Yeah.
So one of the trades that people argue, and I'm not sort of following exactly the internet topology or heads right into it, is that the internet is sort of shrinking.
Yeah, definitely.
So can you comment on this trend and sort of your work?
How it fits in with that trend.
Yeah, exactly. Yeah.
So there has been some interesting work on that. So on the one hand, the internet is shrinking for people like Comcast and Google and probably Microsoft as they try to get more direct connections, things like that. It's also, if you look at the median path length, I don't think that has changed that much, and that's a lot because the internet is also expanding into, say, developing regions and things like that where they're not going to have this really rich connectivity. So any particular path may have gotten shorter, but paths distributed across the internet haven't necessarily gotten that much shorter. I actually think that this work fits pretty well into both those trends. One issue with this sort of collapsing topology of the internet that you brought up is that you sort of have less visibility into it. It's hard to measure these peering links unless you can only measure these peering links if you have a vantage point either down here or down here. If your vantage point is out here, you're not going to be able to traverse that just because of policy. They're not going to export that link. One thing that we show in the paper is that you can start observing more of those links if you actually have reverse traceroute information, because you can sort of inject packets into the middle of that using spoofing and observe more of those links. So I think that this helps give visibility into parts of the internet that maybe are hard to see with traditional techniques. I think the other interesting implication of both these trends, like the collapsing topology and then also expanding the developing region, is that both of those tend in certain ways to make the internet a little bit more brittle. If people are getting rid of their tier 1 providers or having fewer tier 1 providers because they're connecting directly, suddenly they don't have this essentially backup path where they can fail over to the tier 1, and it's much easier to start partitioning pieces of the internet off. So I think that it becomes important to have these debugging tools and tools that give visibility into those parts of the internet, because even as they improve performance, they don't necessarily improve the resilience of the network.
Sure, you got it.
Yeah.
I'm curious, just to hear, what are your next steps? More interdomain or more something else, or what's your longer term plan?
So I missed one part of the question. What domain did you mention?
More into domain work or more some other stuff?
So I'm interested in looking at sort of both types, both continuing in the space and then also expanding into new spaces. So I talked today about how you can use reverse traceroute to get visibility into sort of the round trip path. So I only had visibility into half before. Now I can observe the round trip path and start.
What if we ignore reverse traceroute or reverse path? What others?
So all I was going to say is that we're starting to build up these reverse path maps where you can observe suddenly the routing of the entire internet, and that lets you. It's not so much about having reverse that it's reverse traceroute. It's that it gives you a view into complete routing of the internet. And so I want to start using this new visibility where now I can see how everybody routes to me. I can start seeing the routing decisions that they're making and reason about what paths they weren't choosing that they might have selected, and sort of use this to answer questions about what policies are available on the internet, what policies are in use, what are the cause of particular routing changes. I'm also interested, I think I'm going to continue on in the internet measurement space as well. I have a number of ideas along that, but I also want to use my experience in interdomain routing to start addressing other questions. So as we move towards having more services, more data in the cloud, we're going to have this need for high availability and high performance. And one part of that is these troubleshooting tools that I've talked about, but I'm also interested in looking at other questions that arise in that space. What type of network knowledge do cloud services need in order to optimize their use of the internet? How can we provide that information to them? They're not necessarily going to have the internet expertise because they're sort of outsourcing that to the cloud infrastructure. How can we give them access to that information in ways that they can reason about? There are also a number of emerging challenges in the internet. So the collapsing topology is one. Mobile. I'm interested in sort of starting out from this interdomain space and expanding into those other spaces using what I know here to start, mobility challenges, for instance, are going to require addressing interdomain problems, but they're also going to require addressing problems at other layers. I'm interested in moving into those spaces.
Cool. Well, thank you.